So they say that if you cannot refute something, maybe it's worth taking seriously. So hello everyone, I'm Rahul. I'm a fifth year PhD student at the Indian Statistical Institute in Kolkata, which is in India. And my research broadly focuses on the current tensions and anomalies in cosmology. So I'm particularly interested in using new statistical and computational tools to better understand what might be going on. So I approach this from a few different angles. One is testing beyond lambda CDM models against current data sets, like the work I'll be presenting here. Another is forecasting what future surveys might tell us and studying how different cosmological parameters interplay with each other. So that's a bit about what I do, and here I'll focus on one particular direction, which is interacting dark sector models. Now, I know dark sector interactions tend to split the room. There are people who find them exciting and others who think they're completely unphysical. That's perfectly fine. I'm not here to convince everyone or to take sides. What I want to do is something simpler. Explain why people even consider these models and what do the latest observations say about them and what we find when we test them carefully. So, one of the most remarkable things about modern cosmology is that we can describe the universe extremely well using just 6 parameters, the lambda CDM model. Now, it fits the cosmic microwave background, large scale structure, and supernovae observations remarkably well. For most purposes, it works beautifully. But when we start comparing high precision data sets, small cracks begin to appear. The most well-known ones are the Hubble tension and the S8 clustering tension. And by now, these are not small discrepancies anymore. We are talking about several sigma differences. So naturally, we are led to a very simple question. Is something wrong with the data, or is lambda CDM incomplete? And since I don't want to offend observers here today, let me take the second possibility seriously and look at extensions beyond lambda CDM. Now, there are many extensions: early dark energy, modified gravity, additional relativistic species, and so on. In this talk, I will focus on one particular class of models where dark energy and dark matter interact with each other. But why consider interactions at all? There are two main reasons. First, from a phenomenological point of view, these models have shown some promise in alleviating some cosmological tensions, especially the Hubble tension in certain cases. Second, from a theoretical point of view, there is no fundamental principle that forbids interactions within the dark sector. We simply do not know enough about the dark energy and dark matter to rule this out. In some contexts, these models have also been explored in relation to the coincidence problem. So, the goal of our work was to test these interacting scenarios using current cosmological data and to see whether they genuinely help with any tensions. Now, how do we actually model these interactions? Formally, there are quite a few equations involved, but the underlying idea is simple. We start from the standard continuity equations for two fluids and introduce a phenomenological interaction term which we call Q that allows energy exchange between dark energy and dark matter. Now we take this interaction term to be proportional to the dark energy density. This choice is not derived from first principles, but it is widely used and historically shown interesting phenomenology. We then derive the corresponding perturbation equations, implement the model in the Boltzmann solver, and we run MCMC analysis to constrain the cosmological parameters using observational data sets. We constrain the model using CMB measurements from Planck 2018, supernovae data from Pantheon Plus, and baryon acoustic oscillation data from SDSS DR16. So this part of the analysis was done before the DESI results became available. Now, interacting dark energy has been studied quite extensively in the literature, but our analysis differs in a few important ways. First, we allow dark energy to be dynamical. Many earlier works fixed it to a cosmological constant or assumed a constant equation of state. Instead, we explored multiple parametrizations such as CPL and JBP to look for trends that are robust across different models. Second, there is a technical issue that arises in the perturbation equations. Certain terms contain a factor of 1 plus W in the denominator, W being the equation of state of dark energy, which becomes problematic near W tending to -1. So in order to avoid any divergences, we split the parameter space into two regimes. One with W less than -1, the phantom regime, and one with W greater than -1, the non-phantom regime. And we analyze them separately. Third, some combinations of parameters can lead to instabilities. In many studies, theoretical priors were imposed to avoid such regions. In our case, we chose not to impose strong priors and instead allowed the MCMC to explore the parameter space freely. Of course, unsurprisingly, the chains naturally avoided unstable regions. So in that sense, the data itself enforces stability. The overall philosophy of our approach is to minimize theoretical bias and let the data guide the conclusions. So what do we find? Well, this is the main result I want to highlight. In the phantom regime, interacting models naturally reduce the clustering parameter sigma 8 without worsening the Hubble parameter. Let me unpack that a bit. So we find that the interaction parameter Q prefers positive values in the phantom regime, which corresponds to an energy transfer from dark energy to dark matter. We also see that the usual correlation between H0 and sigma 8, which is present in non-interacting models, becomes somewhat weaker. More importantly, the interaction parameter itself shows no strong correlation with H0, but it is negatively correlated with sigma 8. In other words, as the interaction strength increases, sigma 8 decreases while H0 remains largely unaffected. This is interesting because many models that attempt to resolve one tension tend to worsen the other. Here we do not see that trade-off. While this obviously does not solve the Hubble tension, it does help ease the clustering tension to a certain extent. And this effect is particularly pronounced when dark energy is dynamical, particularly the CPL and JBP cases. So these are the contour plots shown here to illustrate the relationships across different models. I'll not go through the detail of each of them, but the key takeaway is the trend that I just described. So we then explored a couple of extensions to the study. So first, we allowed the sound speed of dark energy perturbations to vary rather than fix them to 1. So in this case, the data does not provide any meaningful constraint and simply returns the prior. Second, we allowed dark matter to have a non-zero equation of state in order to test for possible signatures of warm dark matter. Again, the results remain consistent, very strongly consistent with cold dark matter. Next, we included redshift space distortion data. Now, this leads to tighter constraints on most parameters, including the interaction strength, but the alleviation of the clustering tension becomes slightly weaker. Now, we suspect that one possible reason could be because RSD analysis often assume a lambda CDM framework, which could introduce some bias, but this is something we are currently investigating further. Oh, and finally, we updated the analysis using the latest DESI DR2 BAO data. So this dataset significantly tightens the constraints on all cosmological parameters. We also find that the evolution of the dark energy equation of state is somewhat less steep compared to the non-interacting cases. However, at present, we do not allow crossing of the phantom divide in our analysis, so a direct comparison with the non-interacting DESI results is still a work in progress. So we are developing a consistent treatment of phantom crossing in interacting scenarios that can help us draw a direct comparison with the DESI results. Looking slightly ahead, we have also begun exploring this in our recent work, where we study interacting dark sector models in the post-reionization era using mock datasets from upcoming surveys like the Square Kilometre Array and Euclid, combined with current cosmological data in a full MCMC forecast analysis. What we find is that these future observations can significantly tighten the constraints on interacting dark sector parameters, particularly the interaction strength and the dark energy equation or state parameters. In fact, the improvement is substantial compared to current constraints from Planck, DESI, and Pantheon Plus, with SK, especially in its later phases, providing orders of magnitude improvement in projected bounds, and Euclid achieving a comparable level of precision to early SK configurations. So, to summarize, interacting dark energy dark matter models remain a viable and interesting extension of lambda CDM. In the phantom regime, they can reduce the clustering tension without worsening the Hubble tension. However, precision data, particularly from DESI and upcoming observations from the SK and Euclid, will tighten the constraints and limit the available parameter space. This leaves us with an exciting possibility. Would future data show hints of new physics in the dark sector, or would lambda CDM be the model of the universe? Whichever be the case, at the moment, I like to say that tensions are bad, since they make us cosmologists look bad, but they also keep us employed, not to mention keep our lives interesting. So before I close, just a brief note on what else I work on. So I am broadly interested in cosmological tensions and anomalies, as I already mentioned, including using novel computational tools such as machine learning approaches for reconstruction as well as for forecasting. If any of that sounds interesting, please feel free to reach out. I'm also really thankful to the organizers for this lovely opportunity, and I very much look forward to hearing your opinions and suggestions. I'll do my best to answer any questions you may have during the discussion sessions. Thank you.